Once we have created a frame to be sent on to the communication channel, errors could arise. Of course, we incorporate error detection and correction mechanisms, but we also need to understand the impact and the underlying implications if the errors take place either in the header, the flagging bits, the CRC itself, or the payload. In this module, we shall understand the framing that is affected with errors if flagging is used, that is, flag bits 0, 6 ones, and 0 is used. And what is the impact on the error detection capability? We'll see that through an example. The reference that I've chosen is by Bertzicus and Gallagher. The typical problem that arises with framing is that the errors are going to affect one or all parts of the frame. When errors corrupt the frames, the information that gets directly influenced could be either the flag bits, which mark the start and end of the frame, the cyclic redundancy check as the error detection mechanism, or the length field. Now we are going to see that interestingly, although the error affects one of them, but the underlying implications arise such that the effect of error in one of them has indirect effect on other parts and their interpretation. For instance, if there's an error which occurs in the flag at the end of the frame, because the flag occurs at the start and towards the end. So if an error occurs in the end flag, the receiver would not be able to detect the end of the frame because it is going to consider this corrupted flag as part of the data and would assume that the frame is still continuing. Consequently, the CRC which was preceding the flag towards the end of the frame is now not detected. Only when the next flag is detected, which is the flag of the subsequent frame marking the start of the next frame. So when the next flag is detected, the receiver assumes CRC to be preceding that. But we know that the next flag is the start of the next frame, and anything preceding that would be the idle filler bits. Now this perceived CRC might be the actual CRC for the following frame, but in reality it could also be the filler bits, which is nothing but random garbage data. So the receiver interprets 2 frames in place of 1. The problem is exaggerated because now receiver not only misinterprets 2 frames as 1, but also fails to detect that the error has taken place. An interesting relationship can be mathematically formulated as 2 to the power minus L, where L is the length of the CRC. So the likelihood of error increasing is when we have less number of bits in the checksum or the CRC. With an increased checksum, we see that the probability that an error goes undetected is reduced. Now let's look at a false flag example. Assume that the sent data was 010011 0111 Because of error, the received bit pattern now includes the flag bit pattern as well. So the bits before the perceived flag are interpreted as part of the CRC. This is actually termed as the data sensitivity problem or the extreme vulnerability problem of the data link control. What we understand is, even though the CRC is capable of detecting any combination of errors, for instance, if the CRC can detect 3 or few number of bits in error, a single error that converted the data part into flag actually has either created or destroyed a flag and resulted into a special combination of data bits to satisfy the preceding CRC, because it has created an error that looks like flag bits. This kind of error goes undetected. We shall see various mechanisms which help us to counter this tricky problem.